Good afternoon. We left when we had our work done, doing the same as, look at the half and this was for which kind of distribution? So we shall move on. And this was electrostatic energy. So we move on and look at applying Gauss's law. Divergence of E is equal to rho of epsilon naught, implying that we get that rho is equal to epsilon naught multiplied by the divergence of E. If we can try now to replace the charge density in terms of the permittivity and the electric fields, and this would imply that our work done would be the same as epsilon naught over 2 integral over tau V divergence of E, then integrated over the volume tau. Consider the vector identity. Consider the vector identity divergence of EV equal to V in divergence of E plus V that grad V. You don't worry about this. If you have checked on the on Muele, you find that there is a part of identities as one is part of the cover on the cover page of the book, the Griffith book, and it will be provided in the exam and the tests. So the identities, I don't need you to remember cram anything about identities. The tau in spherical coordinates, the tau in cylindrical coordinates. You don't need to remember anything of that nature. You need to just recall them by seeing them. So identities will be provided as a page in exam and tests. So that's why I'm not bothering you about the vector calculus which you did in your mathematics. On the other hand, the grad V is minus A. If you remember from this expression we derived earlier along in the course, thus we can have a new way of stating our work done as being the same as epsilon naught over 2 integral over tau. And then we have our, instead of our V divergence of E, now we shall be having it being equal to the divergence of EV minus E direct with grad V. You may ask, V is a scalar, how can it be direct with the E? But remember, our grad operator, del, is the same as Kali by Kali X, I plus Kali by Kali Y, plus Kali by Kali Z, K, or you could have used X roof, Y roof, and Z roof for when you take the X, Y coordinates. So then this would be the same as divergence of EV, this one here, integrated over the tau, minus E dot V, so minus epsilon naught over 2 integral over tau, E dot grad then the tau. So, once we have now introduced all this and forgotten about the existence of the charge density, so that we carry out, it is easy to deal with potential and also to deal with electric field density, because we know once we have one, we can get the other. Simply because when we have V, we can get E from E minus grad V. And depending on how many dimensions you are taking or talking of, this could have been minus Kali by Kali X V if you only had the X component. So it's easy to get this. And if you had E, you can get the V as being the integral of E at the end. So it's crucial that once we get either the potential or the electric field, we can then find the other, depending on which we got. So applying the Gauss's divergence theorem, which we normally apply when we are transforming from the volume to the surface. And we apply Stokes' theorem to transfer from where to where? So our work done will be the same as epsilon naught over 2 integral. So I put it, since it is common to both of this, it is common here and common here. So I will say integral over the surface S VE dot ds plus integral over the volume tau E dot E d tau. And I close my brackets. Take a surface S to be a spherical surface. A spherical surface of very large radius, and noting that the electric potential values as below. We have that the potential values as 1 over R. We know that the electric field density is Q over 4 pi R squared, so it varies with or as 1 over, can take the magnitude as 1 over R squared. And we know that the area, yes, varies as R squared. After noting this, I hope you are fine with this. It's just a matter of substituting for when we change this, the substitute for V divergence of E, which is this one here, it was equal to this minus that. We put it in, and when we came here, it meant that we have our epsilon naught on the outside, and then we use divergence theorem to find that the divergence of EV tau was changed to E dot. Yes, the vector which you are trying to take the divergence, you can dot it with the S, and you will have used the divergence theorem. And then the other part, we substituted for the grad V as minus E. That minus came here and made it a plus and got an E dot E. This one here, and of course, which will eventually be E squared. Magnitude of E times magnitude of E, cos of the angle between them, and the angle between them is 0. Okay, so we got that, we see that on carrying out the algebraic gymnastics, the product V, E, and S would be the same as, or would vary as 1 over R times 1 over R squared times R squared. R squared is gone, and we have this whole product varying as 1 over R. And we say that if we take a very large radius sphere by taking a spherical surface, then this will tend to, which tends to 0 as the radius of the spherical surface becomes huge and huge. Hence, we would have that our work done will be the same as epsilon naught over 2 integral for all space E squared d tau. I normally ask this, show that the energy of a given spherical, a given charge distribution is given by epsilon naught over U squared and tau. It's a common question. Whether I bring it or not is not the issue here. So let's take an example to get a feel of how to apply this. Find the energy of a uniformly charged spherical shell of total charge Q and radius R. In other words, if you took your basketball or football and you take the charge to be just the part of the shell, part of the outside cover, and you take the shell, the leather, or the rubber for the basketball to be consisting of the charges. But when actually the total charge of this whole spherical surface being the same as, or spherical shell being the Q, and your shell having a radius R. So let's find this solution as if we took this shell So I'm taking like a basketball that is running in on the bar, and we are having the leather to be consisting or constituting the total charge Q, and this spherical shell is having a radius R. In order to find the energy, we got this energy by looking for, by applying Gauss's law. So we do the same, and let's take the Gaussian surface to be on the outside. Because in order to apply Gauss's law, we must have spherical symmetry. So we take a sphere around our shell, and let our sphere be half thin, or let it have a radius small r, and we have our electric field intensity radial outward from the center of the shell, as if we were to be far away from the shell, our spherical shell would appear as if it is a point charge. So we take it to be coming from the center, and this is our Gaussian surface. Now, Gauss's law states that the integral of a closed surface S, E ds, is equal to the total charge enclosed divided by epsilon naught, the electric field intensity, the permittivity of that medium. And our spherical shell is in free space. As we can see, we haven't been given any other alternative. It's just there in space. So our integral, that is by Gauss's law, our integral E ds will be the same as our total charge small q divided by epsilon naught. And what we mean by the surface here, which we are talking about, is the Gaussian surface. So the total area, because the electric field intensity is the same, we cannot integrate it. The electric field intensity due to this shell is the same, and that is the much that meets this mathematically fictitious surface, our Gaussian surface. But what changes is the area of this surface, and this is where we get our E the spherical, the surface area of the spherical Gaussian surface, which would be 4 pi small r squared. This would be the same as our Q of epsilon naught, and because the electric field intensity is radial outward along the radius of the Gaussian surface, we can use our R roof, R cap, to show where our electric field intensity is. The idea behind is that if we can get this electric field intensity, so can we get the energy. So once we have our E, we know that energy is epsilon r over 2, then we have all space. So for this case, we have a spherical shell. Then we shall have our E squared now. So now I put in our things, and this would imply that our E is equal to Q over 4 pi epsilon naught r squared r something which is similar to the electric field intensity due to a point charge of a charge small q. And then I now can apply my idea to make sure I fit within the energy equation, so that I first get the E squared. So this would imply that E squared is equal to Q squared over 4 pi epsilon naught squared r to the 4. And thus our energy will be the same as epsilon naught over 2 integral over tau Q squared over 4 pi epsilon naught squared r to the 4 d tau. So this is where you'll be enlarging the identities which will be given in your test. That d tau is equal to r squared sine theta dr d theta d phi. It is an identity when you go in the brief on the either use the and even on where I put them there, and also in the brief you can photocopy that first page and last page. I'll always give them in exam. You don't need to cram that the tau is this, it will be given in exam. And as you know that for our spherical coordinates, if you took the equatorial plane to be where our axes lie, if this is our z, and this is our y, x, this is equatorial plane. I give you slice and already know too. There is one angle which goes around the equatorial plane. So for any given point on the surface of this sphere, growing from a small sphere to a big one to a huge one, that point you have the distance from the center, or what we call the origin, is called r. Okay? Now that r makes an angle theta to the z. Okay, or the zenith, if you wanted to take this as the r. And if you chopped off this kind of part, this part here, if you chop it up, you'll be getting an angle which goes around the equatorial plane as our phi. Whereas when you talk of the cylindrical coordinates, which we shall meet shortly in the course, the comparatively, you have that this is your cylinder, I completed, and then you have your y, your z, your x. Along the either cross section of the cylinder is where you get your phi. But if you took any point on your cylinder, the distance from z to the sides of the cylinder, because your cylinder grows large with the time, so you have the z, if you go to where you see those animations, you have your z growing upwards and downwards, if you twist it and going to the negatives. So the angle this plane makes to complete something cylindrical is what we call, so I'm going to take a given point on the sides. So when I take that point, I have that this is the phi here, the angle it will be taken to go around the cylinder or the bottom or top of the cylinder, the distance from Z to the sides of a given formulated cylinder is the R. In some books, you'll find them using rho. Griffith suggests that we can use the underutilized denotation of S. Just because we know that rho is the volume charge density. R, when now you are trying to figure out the comparison between the spherical coordinates and cylindrical coordinates, you now get confused. R here says from the origin to the point of interest, where at that point P is now your R, theta, phi. Now then when you say a point here, you are talking of R again, and then you are talking of the phi here, and then the Z. It gets kind of confusing. So some books, they use rho, and in Griffith, we prefer using S. So that's how the notions will be different. So this plane here sweeps through the angle phi to complete. So that's why we say phi goes from 0 to 2 pi. And then you have the Z, this Z upwards here moving from negative infinity to positive infinity. And then you have the R going from 0 to the radius of the cylinder. Could be R or could be if you are going to blow up your cylinder. So if we substitute, this would imply that our work done is equal to epsilon naught over 2. Also Q squared over 4 pi epsilon naught squared are constant. We are not having any change in the permittivity nor the charge. It's the total charge. It's not going to be changing. So you have the Q squared over 4 pi epsilon naught squared, and then you are integrating over the volume. So now we have integral of the tau. But now the tau, over tau, but now tau is accordingly this, the r, the theta, the phi times r squared sine theta in spherical coordinates. So if I multiply this r4 with this r squared, I get 1 over r squared, and I said that r here will be going from 0. So since our shell is radius capital R, you can't go beyond the shell. So it will be from 0 to capital R, and then this would be the R integral. So we have the sine and the theta. So you have sine theta, the theta, the angle theta is replicated. If you slice our orange vertically, this side should be symmetrical to this side. So there is no use in why you should count the angle theta as from 0 to again 2 pi, because you'll be repeating yourself. So we can only measure it from 0 up to when we complete 180. So it will be 0 to pi. And then we now left with our integral from definitely along the coronal plane is where you complete your angle phi. So angle phi is the same as 0 to 2 pi d phi. You don't have any variation in phi as per our expression. So we do our gymnastics, implying that our W would be the same as epsilon naught over 2 Q squared over 4 pi epsilon naught squared. We add 1 to the numerator, to the index, and divide by the new index. So we get minus 1 over r. I don't know why I should do this to the end. You should be able to work out this, since you are good mathematicians and good physicists. So my in the interest of not making you look like you've never done any mathematics, I say that we go on and on to better for what done will be the same as q squared over 8 pi epsilon naught. It shouldn't bring any problems to you. Now, if we are in a given system, and being in a given system, we are talking of the energy within this system, we may not be able to get the energy everywhere at a point, and maybe it may not be equally distributed everywhere, because it may be hard to have an energy, a charge distribution. If we will talk of a continuous charge distribution, it may be hard to get it as uniform. Or, you can't have it within an isotropic medium. That means we should be interested in the density of this energy, because even the charge, we are only interested in the charge density, because you may have this whole slot with maybe 2 charges, you have many charges around here, and then you have some here. So if you want to have this distribution meaningful, you only get interested in the charge density, because that one at least helps you to get what you want. And that's why we are going to look at the energy density in an electrostatic field.
Excuse me.
Yes, please.
That 8 pipes we have 4 square down here. Because they are happy.
I don't know. I said you remember I have something here which may not be so significant, but I believe I'll get something here, and so will I get some. Please continue and finish this. You got a whole afternoon and some part of tomorrow morning, so don't hustle. Just I've stopped here, so go on and input all this stuff. And if at all I have a problem with this and that, then also investigate it until when you get the file, and then we can meet tomorrow. Yes, because you are big enough to be given everything. So the energy required to assemble, please don't argue with this expression now. You got enough time after the lecture to really go through yourself. And it is an example from Griffith, which is on Mwere, so you shouldn't have any issues. And I believe maybe the working is on Mwere in my notes. So the energy required to assemble the distribution, we got it as U equal to a half integral over tau rho v tau plus a half integral sigma v. Yes. This is by definition. you have the energy required being rho v d tau plus, so this is if you look at it in terms of being a volume, and then if you took it as a surface, where rho and sigma are the volume and surface charge densities. Let's say distributions respectively, and V is the potential. If you recall from behind, Gauss's law in electrics was given by rho is equal to the divergence of D, and sigma was given as D dot N. So this is one thing you have to recall, that rho was equal to the divergence of D, and the surface charge density was D dot. If you were to look at the charge density, you would have to diverge within this electric displacement vector, would have to diverge within your volume. But if you are going to take the surface charge density, you have to look at it being normal to your interface. If you remember, your charge distribution, your electric displacement vector has to be looked at how it is going through your interface normally. And we discovered that under boundary conditions, that actually it goes through, it conveys through, or it is conveys from medium 1 to medium 2. The normal component was conveys, whereas for the other part, on the interface, if you took this in terms of the E, then we talked of the tangential component being conveys along the interface. So if we do that, then our definition of our energy required will be, we substitute for rho, so that would be U is equal to a half integral over the volume tau. Rho is now divergence of D, and then our V, the tau, and then we are adding on half integral over the surface S. This is surface S, and instead of our sigma, we put in our D dot N, and then we have our V. Yes. I think now here you can run through like as if it is a piece of cake. So using the vector identity, which I used some time back, using the vector identity, this identity is always given on the identities. These ones I talked about on the list of identities that I will provide within the test or exam, that divergence of a product of a vector and scalar is the same as the scalar divergence of the vector plus the vector, then goes with the gradient operator with the scalar. And this would imply that our U would be the same as a half integral over the volume tau, divergence of D, divergence of D times V is the same as divergence of dV. And then subtract d dot grad V. So that gives me that this is divergence of dV, this one, then d tau plus a half integral d dot E d tau plus the other part which is not affected by the vector identity, which is a half integral over the surface S, and we have VD. I've just rearranged it, and ds. I hope all is well. Since E is equal to minus, because I know most of you are having trouble here. After saying that I will substitute this with this, which is equal to this minus this, so I will have this divergence of dV here, and then I subtract d dot grad V, but grad V is minus E. So I put this one. That minus E comes here, which should have been a minus after taking this one here, and becomes plus. Just trying to jump some steps to make it complicated, so that you have some work to do. If I go step by step, put in the minus, I don't think you get anything to do. At the end of the day, you say this course is very simple. So I just jumped a little bit of steps. Since E is equal to minus grad V, so you have this as d minus D. But when you put it this side, it becomes a plus. You substitute it becomes this a half, which was outside, integral d tau, which is the same as tau here, and we have the S there. Now, if there are no problems so far, then I can use Gauss's divergence theorem . So I can change the volume here to a surface and see how it would relate to the last term. Otherwise, there's nothing much I can do to this other part. So using the Gauss's divergence theorem, divergence of any vector can be taken as that vector done with ds, if I'm transforming from a volume to a surface. If I have integral over the volume tau, divergence of any vector A, the tau, I can change this into a surface being the same as integral over the surface S then A, yes, and I will be done. So let's see what happens here. Our U is equal to integral over the surface S, and then we have our VD or DV. V is a scalar, it doesn't matter whether you put it on the other side or the other side. So we have our VD that N, then ds. Remember, this N the ds vector is always specified by saying that it is normal to the, this vector is normal to the surface. the Benon surface will normally take. And we can only signify its normalness by invoking this n cap. So then we have our ds outside. So I have just planted this n cap inside, just to make sure that you know this is the same as the vector I was talking about, dot ds, the vector, and then I add on a half, and I think there is no way and a half can disappear. Is that all right? So I should be having half somewhere here. I just substituted, transformed the integral. The half should be significantly there. And then I add on a half integral d dot a, then the tau, sorry, over the volume tau. And then I add, the other side I haven't done anything. I add on a half integral dD that and yes, you can put it like this if you want. We have now two things which are similar, half-half. But we don't need to bother about them. We could have added them and we get one of them. Okay? But here is why we can't bother about them. Because in the previous example, when we are looking at the spherical shell, we know that our d, which is always epsilon e, varies as 1 over r squared. Our v varies as 1 over r. Our ds varies as r squared. That is, this is for large distances, from the charge distribution. Just like we took, when we took the radius r to be so huge by taking the Gaussian surface to be as large as possible. If that happens, then we get this and this diminishing to 0. So that we can simply say that hence our one integral over surface S dV than n ds would range as 1 over r squared times 1 over r times r squared is cancelled out, which would be 1 over r, which tends to 0 as r becomes infinity, as you extend away from a charge. Thus, we would have our u. If you want, you can continue and add another step where you only have a half this plus 1 this, because these two are giving you this one. Thus, our u would be the same as simply a half integral tau d dot and then the tau. Does this ring a bell in your mind? If we are in a free surface, if our distribution is in a free space, not free surface, a free space, then our this energy here, if you take our d equaling to epsilon e, our u would equal to a half integral, and then you put our epsilon naught e that e d tau over the volume tau. If you put our epsilon outside, you get integral over tau E dot E is equal to, and we got this a while ago when we were trying to come up with the energy required. So this is the energy, and our heading, if you remember, was that we are interested in the energy density in such a distribution. So what is energy density? Our energy density would be the same as dUd, the change, the elemental energy divided by the charge. So the energy density will be the same as charge density is the charge divided by charge density is given by when we are having our charge distributions and we had our elemental volume, the tau, and what was rho equal to? We know that the tau was equal to dq. So it means that rho is equal to dq by. So our energy density UE is equal to u tau, which is the same as a half d dot. Therefore, UE is equal to a half d. This marks our section of sort of electrostatics. So we now know how to get the electrical density for a given distribution. We know how to get the potential of a given distribution. We need to do some work. If we have potential, we do some work. Once we do that work, we now know the density of the energy we do in putting up together a system. Then what we are left with is now to solve some of the potential problems using Laplacians. Because now we indulge you to read through the book so that when I'm using some terminologies, you have an idea of what is going on. So see you tomorrow at 12. Get permission from me. Before he tells you something, I wrote something here and then I was forgetting. Tomorrow at 2, chemistry students are organizing sort of a career talk with somebody from outside in the chemistry main. So you can, the MOOCs people, I think this one. Did he talk to you or you were feeling so bad that you couldn't listen? Yeah, but very strange. So I let you have fun with him. I hope they won't chase you from here in the next lecture.